Cattle. Ma'am? Ma'am, shall we begin? Andrews, ma'am?
Yes, ma'am. Yes, ma'am. Yes.
Okay, wait, okay. Ma'am, our students will introduce.
Good morning to everyone present here. I, Dharni, on behalf of the Department of Computer Applications, warmly welcome you all to the fourth day of our 5-day faculty development program on quantum computing and its applications. We are grateful to have a wonderful gathering of faculty members, research scholars, students, and industry professionals who are eager to explore this cutting edge domain. Thank you all for your continued participation and enthusiasm. Before we proceed, a few quick announcements for the participants. Please keep your microphones muted to avoid background disturbances. If you have any questions during the session, kindly type them in the chat box. Selected questions will be addressed at the end. Please keep your video turned off. Feedback links will be shared in the chat toward the end of the session. Now, I invite Adini to introduce our resource person.
It's my great pleasure to introduce today's esteemed speaker, Dr. J. Andrews, Associate Professor and IQAC Coordinator at St. Xavier's Catholic College of Engineering, Nagarkoil. Dr. Andrews is a passionate educator and researcher with expertise in machine learning, data science, and intelligent systems. She has been instrumental in fostering research driven learning and has guided several academic and industrial level projects. Today, she will be speaking on quantum computing for machine learning, a topic that beautifully bridges two revolutionary technologies. We are honored to have you with us today, ma'am. Welcome once again. Now, I hand over the session to Dr. J. Andrews. Ma'am, the virtual stage is yours.
Thank you. Thank you for the introduction. Am I audible?
Yes, ma'am.
Yes. Okay. And also, my screen is visible to you.
Yes, ma'am.
Yes. Okay. Okay. First of all, I would like to thank the Department of Computer Applications for giving this opportunity for me to take part in this FDP on quantum computing and its applications. So far you have learned the foundations on quantum computing, and also you could learn the data representation, quantum representation, especially qubits, quantum gates, quantum circuits, and also the quantum algorithms. And today we are going to see another one interesting topic which combine both the quantum computing for machine learning to enrich and enhance the quantum machine learning algorithms and also the models. So in this presentation, I am giving three important components. One is recapping classical machine learning and also the problems in machine learning. And the second thing is what is quantum machine learning, how we can combine quantum computing with machine learning. And then we can see one or two examples, algorithms, especially quantum SVM or quantum neural network, and what are the frameworks which supports, etc. So the first session everyone knows about this one, machine learning. So what is machine learning? Can give the answers in the chat window. Machine learning is a subset of artificial intelligence, isn't it? What is artificial intelligence? So it mimics the human intelligence. Either we can develop a software agent. Whether I am audible to everyone?
Yes, ma'am, you are audible, ma'am.
Okay, okay. Just a minute. My screen is not moving. Okay, so developing a software agent or a machine by imparting all the human intelligence, especially problem solving, reasoning, communication, linguistic intelligence, like all the mundane tasks can be given to a machine or a software agent that behave and act like human as well as and behave and act like a act rationally. So that is the definition of artificial intelligence, and with that motto we are developing so many things and make our day-to-day activity as a easiest one. And machine learning is a subset of this artificial intelligence. Why? Because in a human intelligence, a normal human being is can able to learn, has ability to learn. So that ability we are also imparting to a machine. So machine learning is a subset of artificial intelligence that we are learning from, that a machine can learn from the data. So what is traditional programming language? That is a computer programming language and also machine learning. What is the difference between traditional programming language and machine learning? Can anyone give the answer? So in traditional programming language, it works in IPO's cycle, that is input, process, output. All the instructions, programs, everything will be given or which will be written by the human. So based on that, we can check our input as well as output. Isn't it? That is our traditional programming language. Whereas in machine learning, we are not supposed to give any instructions or commands, or we are not writing any programs. Just we are giving the data. Either it could be input data or it could be output data, or else we can give only input data. With that input data, the machine could learn and it identifies the correlations and relationship among the data and predicts or develop a mathematical model. So especially in this example I have given, this is a linear regression. So here we want to classify all the data points by means of a straight line. So if it is possible, then we can call it as a linear problem or linear data. If we couldn't uh, differentiate with the help of a straight line, we can call it as a non-linear problem. So therefore here we are in each iterations we are giving the value, we are changing the values of m and c such that we could get the best fit or best straight line equation in order to separate all the data points. So for that, we are using some optimizers and also error functions. So this diagram will shows that one. So here we just give the input samples as well as output symbols. Why? Because this is a supervised learning. So based on that, it will develop a mathematical formula, and that mathematical formula can be used in future for predicting new samples to test the new unknown samples. So this is the normal classical machine learning working principle. And again, we have also forwarded to this deep learning. Deep learning is a mimic of a human brain. So here we have billions, 10 billions of neurons in our human body. So likewise, we can also give complex structure to machine to perform the same task like a human being. So in deep learning also, in the past decade, from 2010 to 2025, there are so many advancements, starting with the AlexNet for image video recognitions to till now we have the generative transformers models are available to perform or to predict the data and also to perform the deductions. So this is the classical machine learning model, and this is one typical example. Here, this is a neural network. We can either give the image as an input, or else we can also take the features from that image. In traditional machine learning, we extract the features, and that features are given as an input for the machine learning algorithms like decision tree or SVM or any other machine learning algorithms, and that algorithms will predict the output. So uh, that is in machine learning, whereas in the deep learning, just we can give the image itself, it itself extract the low level as well as high level features automatically and predicts the output. And normally the machine learning is classified into three main categories. I hope this is known to everyone. Like a human being, from the birth to death we are learning, and also we learn by means of these ways, with the help of the teachers, or with the help of our parents, or with the help of our others, with the guidance that comes under supervised learning. And unsupervised learning means we are learning from our the properties by our own, that is unsupervised learning. And trial and error based learning. So if you based on the environment, the happenings around us, and based on that we could learn so many things. If we succeed, we'll get the reward, or if we didn't, we'll get the punishments. So in that scenario also we are learning. So based on that, here also the machine learning is divided into three parts: supervised, unsupervised. In addition, we can also have semi supervised learning algorithm, and then reinforcement learning. So in supervised learning, again it is classified into classification regression problems based on the type of output samples. If it is a discrete, in the sense, we can make it as a classification algorithm, or else if it is a continuous value, if the output value is a continuous variable, we can call it as a regression problem. So these are some of the examples of classification, naive Bayes classification, which works on Bayes theorem. Then decision tree. So here it based on a hierarchical structure, and also entropy and information gain, it works. Then support vector machine. This is a popular and mostly used machine learning algorithm, where it uses a hyperplane to separate a number of data points. Then random forest, like a number of decision trees are combined together and produce a majority voting. Then k nearest neighbor. So here we will group the data based on the nearest points. So this type of classification will come. These are the classification algorithms. And when it comes to regression algorithms, the same thing also we can have as a regression: linear regression, logistic, neural network, SVM, decision tree, ridge, lasso. Likewise, there are so many regression algorithms are also there. And next, unsupervised learning. Here we have the association rule mining as well as clustering algorithm. So a priori algorithm, FP growth, like the data mining algorithms are comes under this unsupervised learning algorithm. And clustering algorithms are k-means clustering, then fuzzy C-means, DB scan, hierarchical clustering, Gaussian mixture. Likewise, there are so many clustering algorithms are there. Here only the input samples are there, but there is no output samples. Whereas in the case of supervised, we have both input as well as output, training, validation, testing phase. Here it's not like that. Only with the properties of or the features of the data points, it will be clustered or grouped. So these are the clustering algorithms. And for reinforcement learning, it uses these learning paradigm to perform decision making. And here we have Q learning, R learning, and time dependence learning, TD learning. So, and again, I have already informed there are so many pre-trained models are available. So why these machine learnings are popular during these times means, one of the important reason is because of the computing facility. We have easily access the computing facility with the help of cloud, or else even with our latest computing facility also we could able to run. So these are the CNN models, starting with the AlexNet. Till now, there are so many pre-trained models like ResNet, GoogleNet, then BGGNet. Likewise, there are so many pre-trained classification models over there. And nowadays, the vision transformers, generative AI transformer models also available for images, videos, audios, etc. So this is one such example. So now the trend is combining the multi-model pre-trained models also available. That is for we can also give input as a text, images, and then also we can give the videos. Everything will be combined, and it can also be trained with the help of the latest combined pre-trained models are there. So the advantages of these pre-trained models are these models are already trained by many persons and also the companies who is having a lot of amount of computing facility. So they train for training. It takes around 1 week or 1 month. They have used their computing facility to train the data, so or train those models, and that trained models are available for open source. We can use those models for our data set also using transfer learning concept. So in transfer learning, we can able to change the input as well as the last three layers of output to adjust or to fit with our classification or with our data set, and we can perform that type of uh, performance that can be done with the pre-trained models. So, and next we can see the important issues in machine learning or else deep learning. The first thing is if the quality of data is poor, definitely you'll get a poor information data output also. And the next second one is underfitting as well as overfitting, that we already know that during the training phase we have less amount of data, or some other reasons it does not perform well. That type of problems are called as underfitting. Another thing, in our training phase with our data it performs better. It produces above 99 percentage accuracy, but when comes into real time it won't give that much accuracy or that much performance. So that is called as overfitting. So these problems can be rectified by means of other methods like regularization, L2 regularization, or they'll use data augmentations, or GAN models can be used to overcome these things. And also data, if you want to develop a better model, we need more amount of data, but it is not often correct for all the cases. In some cases, and it also works with some limits and also some bounds, and all the computations are performed in sequential manner. So that is a main drawback in machine learning. So that's why we are going for quantum computing. We are combining this quantum computing with machine learning. That in quantum computing we are performing parallel processing. So that is the reason for uh, mainly we are switch over, or we are combining quantum computing with the machine learning, and also quantum computing is having uh, the facilities like that is properties like superpositions. So any number of bits can be represented or in superposition state. So thereby they can perform parallel computing. And again here the space complexity, and also in most of the machine learning, even I have already said that to train the complex deep learning models it takes a month, the monthly or yearly, there is a lot of time to compute a single model, and that can be expressed in polynomial or exponential time. Okay, so that could be reduced by means of quantum computing. So that is a main problem. So even when we use the pre-trained models for our own database, even for executing 10 epochs, it takes around 2 to 3 hours. So with the GPU computing, so that much time it requires, even for with 2000 or 3000 images. When you take 20,000 or lakhs of images, definitely with this pre-trained models, we we can't able to do. It takes polynomial time. So that is the main drawbacks in classical machine learning. So this is the first part of our presentation. Next, we are going to see about quantum machine learning. Anybody having doubt on this? Please give your questions here. So the next important component is, or the thing we are going to see today, is quantum computing. So quantum computing is a combination of both. It combines machine learning components as well as quantum processes, quantum information processing. So here it combines the computing methods of quantum and the machine learning algorithms in order to provide or in order to enhance the machine learning algorithms or models. And here it lays on the qubits instead of bits. And in normal machine learning or the computing, we are using a Boolean digital logic circuits. Here we are using quantum circuits to encode the data. And also we are using quantum gates for activations, and also for to get better take the decisions, we are using quantum interference. So this makes the complex data can also be done or predicted very quickly with the classical machines. So here this is the representation of a classical computing versus quantum computing. In classical computing, it is represented as bits or zeros and ones. For example, it is having 7 bits. So we are passing it to the classical machine learning algorithm, and it is computed with the logic circuit, digital logic circuits, and we can get the results. Whereas in the case of quantum machine learning, we convert or we will represent the data in terms of qubits, quantum bits. So, for example, if it is a 7 quantum bits, we can represent 2 power 7 superposition states. So, that can be performed or that can be computed with the quantum algorithms, quantum machine learning algorithm. There are so many frameworks are available for open source. So, we can use those frameworks, and we can also compare our performance with this classical computing, classical machine learning algorithm as well as quantum algorithm. And here they are using quantum circuits, quantum gates, and quantum interference to generate the output. And this is a diagram I have taken from this website, and here it compares a clear descriptions between the classical machine learning as well as quantum machine learning. So let's consider the classical machine learning. This is a classical machine learning pipeline. We are taking the data, and the data can be represented in the low-level language. It is in zeros and ones, bit representation, and it will be pre-processed to improve the quality of the data, and then it is given for mathematical algorithms like all the machine learning algorithms, whichever applicable for this particular problem, we can choose it. And this will be computed, or we can perform a fitting or training of our data, that is by means of fit operations. We can use GPU, depends on the size of the data. We can choose GPU, or even now TPU is also available. From cloud, we can get TPU 100 any number of units. So for example, if you are using Colab, you can get 12 hours free GPU and 4 hours TPU as a free processing unit. Then with the help of that, we can execute number of iterations, and if you make the convergence, we can predict the recognitions, or we can identify the patterns from it. And see here the time, even though we are using the pre-trained models, it takes more amount of time for computing to generate the patterns. In quantum machine learning, what we'll do is, instead of giving classical data, the quantum data is given, and the quantum data is having a very good property called superposition. Superposition is before we can take the measurement, it is a number of superposition states simultaneously, all the possible states. For example, if it is n qubit means 2 power n possible states available. So it will be in all those 2 power n possible states at a time. So in the last class, we have seen based on the reference plane, we can have different decisions while tossing a coin. Instead of taking the decision 0 or 1, we can put a reference plane and we can change the reference plane. We could get number of different positions. So that positions are given as an input to the algorithms. And again here also, if you want any pre-processing, we could do it, but it is now exploring. And we can use the algorithms to train to fit using quantum processing. And based on that, it will predict the pattern. And here you can see the time consumption of time is very small. So when comparing this one, here it takes 3 by 4, here around 1 by 4th of this time. And this is the processing methods. Here uh, when we use quantum machine learning, the classical data that is represented in classical data is represented in bits. So that can be converted into quantum data. So classical data is transformed to quantum data by means of some encoding methods. So we are going to see those encoding methods. So based on that, the classical informations or classical data is converted into quantum bits, and that quantum bits are given to the quantum machine learning algorithms, and then it will be trained, or they will develop a based on the data, it will fit on those and it will develop a model. So here, if suppose there is n bit 3 means 2 power n, 8 possible states are available, and those 8 possible states of different data are given as an input for the quantum machine learning. Finally, you'll get this one, and it is given as an output. And these quantum machine learning, like the deep learning applications, it is also used in face recognitions, the entertainment services, gaming, self-driven automations, finance, recommendation systems, genetics, medical, healthcare. Likewise, in all the domains, you can also use this one. So those are doing research. So you can compare your traditional machine learning models with quantum machine learning models, and you can analyze the performance. There are a number of papers also available. And mainly the quantum, this we have already seen, it is represented in classical bit. And this is the qubit representation. Here, like the number of planes, based on that, we can represent the qubits. And the qubits can be represented by a format called Kate's notation. This is a notation. This is normal value. This is Kate's notation. And this is the probability. Along with those kit value, we will have the probability also. So mainly this quantum algorithms are developed to solve problems in machine learnings. So especially the time consuming, or even for each and every machine learning algorithms, there is a main complex complexity area will be there. So that can be enhanced with the help of quantum algorithms. And we can also use quantum computers to implement or enhance the machine learning algorithms. Then we can improve the learning theory. We have seen the learning paradigms like supervised, unsupervised, and supervised. So that learning theory or the model behavior can also be improved with the help of quantum principles. And again, we can also make a hybrid method of quantum and classical architecture in order to improve the training as well as to predict the interference, or to inference means prediction, to predict correctly. So this is a mathematical representation of n qubits. Here, if it is a single bit, it is either 0 or 1. Here, it is in superposition state. 0, 1 in all the combination, it is in superposition state until we can take the measurement or decisions. And this is multiple bit notations. And mainly this task in a quantum machine learning. So this is the core component. That means Q for C. Q for C in the sense quantum processes are used to process classical data. So here comes the quantum machine learning. So we are giving in machine learning, we will give the classical data. The same classical data we are giving to the quantum processor to perform or to predict the same thing. So that is quantum processor for classical data. Then C for humans, classical processes to analyze quantum data. So this quantum data is represented in this format. And Q for Q in the sense quantum processor could use for quantum applications or quantum data. And C for Siemens, classical data which can be processed by classical processes. So here we are going to concentrate on this part. Quantum processor for classical data. So we are giving the input as classical data, and that is encoded to quantum bits, and it will be processed with the quantum algorithms, and then finally it is given the output as a qubits. Again it is decoded to the original classical informations. So this one is a quantum machine learning. We are going to concentrate on this one. And these are some of the learning paradigms, the same learning paradigms what we have in the classical machine learning. The same thing here also we are going to use. And these are the learning tasks. So either it could be a discriminative learning or it could be a generative learning. So in our learning algorithms, we can have these two tasks. One is identifying the classifications, otherwise it will generate new samples based on the original. That is generative A will play on this one. In generative A, we have two components. One is a generator, another one is a discriminator. So based on the input, it will generate a false information, and the task of discriminator is to identify whether it is a false or it is a correct one. So when the generator overcomes the discriminator, then that as a final output to give the generative details, generative AI informations. So based on that, it works on a deep phase or deep. What all the generative applications are working on this things, and these are the applications areas like quantum machine learning in chemistry, computer vision, logistic, finance, health, in all the areas it is also using. And the progress of quantum computers. So evolution and progress of quantum computers. So this I have taken this from this article. So here IBM has developed 156 qubit so far. That is the highest one, and this is a system name. And these are all the other number of qubits. Initially in 2020, 27 qubits computers was developed by IBM, then Honeywell, then Continuum. Again, IBM is having 156 quantum bits of computers. So just imagine 2 power 156 superpositioned informations can be processed in parallel at a time. So definitely it is the performance is very high for normal classical computers. It takes thousands of years to compute. That could be processed within 2 to 3 years. So that could be the processing speed. And this processing speed can be calculated using a matrix called circuit layer operations per second. Normally, the general classical computers are calculated using million operations per second, isn't it? So here, the quantum computers are measured in terms of circuit layer operations per second. How many operations are performed in each circuit layer, because it deals with the quantum circuits, quantum gates. So therefore, this is the metric for the quantum computers. And this is quantum computing properties. I hope that you have already seen this one. Even then, I could able to refresh it. So what is quantum? What are quantum objects? So please give the answers in the chat window. What is quantum or quantum objects? So any object which is having 10 power minus 8 centimeter, and that type of objects are called as quantum objects in the quantum world. Let us take an example. We have a 1 centimeter scale, and that 1 centimeter scale is divided into 100 millions of pieces, and each pieces are called as a quantum object. Are you able to assume 1 centimeter uh, uh, width of scale, and that is broken down into 100 millions of pieces. So therefore, each piece is called as a quantum, or that tiny particles are called as quantum particles or quantum objects. So that much small things are possible in quantum computing, and it possesses the following properties. The first one is it will behave like a particle or a wavy nature. That is called a dual nature. So when you throw a ball, it is having both wavy as well as particle nature. When a ball is in rest, it holds particle. When it is in movement, it possesses the wave nature. This same thing here also, the quantum particles or quantum objects will have the dual nature. Sometimes it may be in wavy nature, it is in particle nature. So it is very hard to predict. And the second important thing is quantum entanglement. So what is quantum entanglement? Suppose we have two correlation among quantum objects, and one object is resides here, and another one is in New Delhi. So therefore, with the influence of, or with the present state of superposition property. So 0, 0, a qubit can be in all the four states 0, 0, 0, 1, 1, 0, 1, 1. So all the four states are at a time matched with the values. Immediately, with the help of quantum interference, we can identify the best decision along with the probability. So, which is the best one, we can easily identify with a single attempt. So, just assume this is 2 power 2, 4 bits. So, as we have seen in the previous session, the
Ma'am, your presentation and voice is not breaking. Ma'am, you are not audible, ma'am.
ma'am, just wait because of network connectivity. Again, I have
Okay,
re-logged. Just wait, ma'am.
okay, ma'am. Okay, go ahead.
Ma'am, whether it is visible? Shall I continue?
Yes, ma'am, you are visible.
Okay. So we are discussing about. Sorry for the interruption. So there is a problem in the network issue. So here we are discussing about the quantum computing properties. The first properties, I have already said that in the quantum world, each and every particle is having 10 power minus 8 size. That much tiny scale is available. So it will be in both the wave as well as in particle nature. So dual nature. And the second important property is quantum entanglement. That is, if two or more quantum qubits are correlated, with the help of one qubit we can easily predict or predict the next one, even if it is in far away from us. So that is easily used, that quantum entanglement is used in communication purposes. Then superposition, so this is very very important in our machine learning. Why? Because I have said already. So in order to search an element, um, suppose we have four elements, and all the four elements are represented zeros and ones, and if you want to search any element among the four, we need to perform at least, in the worst case, four times we have to perform comparison. Whereas in the case of quantum computing, the qubits, a single qubit itself, we have 2 power n bits. That means all the 4 bits are in the same qubit. With that single hit, or with a single search, single time itself, we can able to identify the exact key element. So that is possible. So that is the main advantages of using uh, quantum in machine learning. So here we have given the examples. One bit qubit means the qubit register is having 2 power 1, 2. So here the 0 and 1, the 0 and 1, they divided by root 2. And if it is 2 bit means 4, therefore 0, 0, 0, 1, 1, 0, 1, 1. All the four combinations. In superposition, a qubit is having 2 bit 2 qubit is having four elements in the superposition. And this is the probability 1 by root 4. And for 2 power 3, it takes 8. Likewise, it goes on. So I have already said that in the previous slide, uh, IBM, the latest IBM has introduced 156 qubit computers. So therefore, just assume we can process a huge amount of information within a second. So that could be possible with quantum computing. And the next important property is tunneling. So that is also used in machine learning, where in the sense uh, optimizes gradient descent to reach the local maxima or conference. So local maxima are the local to reach the global maxima. So even with the quantum objects, if it doesn't have any energy to reach that destination, it can reach it. So with the help of tunneling, we could achieve that one. So especially in optimizers, gradient descent optimizer, Adam optimizer, there are so many optimizers we are using there. So this quantum object can easily travel or without any sufficient energy can reach the maxima, local maxima or global maxima. And when we measure the quantum object, definitely the object characteristics will be changed. So before measuring, it will be in all the superposition states. So I hope that this property already you have seen in the first 2 days. And this is the comparison of time complexities of machine learning algorithms, which compares both uh, classical machine learning as well as quantum machine learning. And I have taken this one from this article. So here, these are all the machine learning algorithms, uh, even deep learning algorithms also there, regression, linear regression, decision tree, SVM. So in all the cases, you see this, this is a classical computation, time complexity, that is, it takes order of n for linear regression, and for Gaussian, there is a more amount of new mathematical linear operations will be there. So it takes order of n cube. For decision tree, it is n log n. Ensemble methods log n. Support vector machines, it ranges between approximately, it lies between order of n square and order of n cube. Then these are the other representations. So here mostly all the algorithms is having the complexity of polynomial or exponent amount. So here in this case, variational autoencoders, it even it takes an exponent amount of time, so e power n. So therefore, it is very high. But it just compare it with the quantum computers for linear regression. It will be in logarithmic, log n, log 2 means log 2, order of 2 means it is here order of log 2, that is 0.03. So that much reduction is available. This is the gradual or reduction in quantum computing that is compared with all the methods, and it is proposed here. And already we have seen the problems in machine learning, so how to overcome these problems. So the first one is it can easily perform all the linear algebraic operations, especially in all the machine learning applications. We are using linear algebraic operations like matrix operations and other uh, operations. So that could be done in a fast manner with the help of quantum speedup. And it has basic linear algebraic subroutines, quantum basic linear BLAS. Using that, we can also able to do it. Then all the Fourier transforms, eigenvalues, vector determinations, and solving the linear equations. So all those things can be easily performed with the quantum computing. Especially all the exponent quantum speeds can be converted or reduced to logarithmic comparisons, and so therefore it is used in trainability. The training time will be reduced, and also it is generalized for all the applications. Just you can assume here, and all the machine learning applications there is a drastic uh, time delay, sorry, time, what a reduction in the time. So that could be observed here, and also the computation complexity also reduces. So in each machine learning algorithm, so there is a core computation complexity component. So we identified that computation complexity component, and we can give that one with or we can use that one for quantum machine learning, or quantum machine learning algorithms to perform those computation tasks in parallel. So thereby we can reduce it. And I have already said that the qubits are represented in superposition. So therefore it takes different parts of computation at the same time. So uh, in the previous example, the search example itself, I have said that the single qubit, sorry, two big qubit has four elements, and all the four elements are parallelly compared with all the key elements with available in the search array. So therefore, it performs parallel computations, and we can get the results very quickly. And here, high dimensionality with a relatively small number of qubits. We can even represent a high dimensions of data with a small number of qubits. Then quantum machine learning takes logarithmic time in both, that we have seen in the previous slides, and there is an exponential speed up with the quantum algorithms. So in these ways, the quantum technology or the quantum computing will impact with the machine learning algorithms, and we can get the results very quickly instead of going for increasing the GPU or computing facilities. Or if we are going for increasing the complexity of the algorithm, we can use quantum to get better results. And these are the comparisons based on the parameters. Definitely computation cost is high in classical machine learning, whereas in quantum machine learning it is very low. In future also it will be reduced. That type of research is going on. And in the classical machine learning, overfitting, it is common, depends on our data set, quality of data set, the quantity of data set. We can have we can come across this overfitting problem, and we can also avoid this one. So that is also possible, but it is under research for quantum machine learning, how to reduce the overfitting. And the dimensionality is a major issue. When the dimensions are increases, definitely the algorithms slow down, and also we didn't get the uh, so one of the persons given the query is what programming languages, ma'am, that we will see in the coming slides. There are so many tools are available by IBM, Google, TensorFlow is itself. We have things, and also using quantum programming languages, we can do it. Then the training complexity, sorry, scalability is limited in classical, whereas in the case of quantum machine learning, it's up to the limitations of hardware component. Then training complexity is high in classical machine learning. Whereas here there is only one problem, that is a drawback of quantum machine learning. If the flat surface, flat plateaus, the same amount of cost is also utilized for those things. And also with respect to hardware noise, it is also there. Then interpretability, it is hard, but in quantum machine learning it is very hard. And data encoding in classical machine learning, it's not needed, whereas in the case of quantum machine learning, that is a major problem. Why? Because we need to convert the classical data into quantum data. So therefore it's a major problem. Then algorithm maturity, that is usage of the algorithm, this is stable. Why? Because all the mainly most of the machine learning algorithms were used in many applications, and they proved it is good, and it is used for many cases. So whereas in quantum machine learning, it's an emerging field. We, the researchers, we have to analyze and we have to give the comparative with the classical as well as quantum machine learning algorithms. These are the benefits of quantum machine learning. So quantum machine learning can speed up the training time. I have already said that for pre-trained models, with the pre-trained models, and even for 3000 data for 10 epochs, it takes around 2 to 3 hours. Whereas if you are using quantum computing with qubits, it could be reduced. Then quantum machine learning can also use quantum tunneling to get pure objective, that is gradient descent. Then it also used a more complex network topology. Then we can also adjust that is in machine learning we have hyperparameter tuning. So that is a separate area to tune our all the parameters which is involved in the algorithm. Thereby we can get the better results. Here it will perform adjusting all the hyperparameters automatically, and also it performs all the complex matrix tensor operations with a high speed. Why? Because it is in push with, because of the superposition property, it we could perform this type of manipulations very easily. So this is the second part of our presentation. So first we have seen the basics of machine learning, and also we have seen the recap sessions of machine learning. And second component is quantum machine learning. So that also we have seen the properties, why we are using this quantum machine learning to our classical machine learning problems, how it addresses the main advantages, time, that and also it will give the computing facility easily instead of that one, the GPU computing or TPUs. So next we are going to see the third important components or the implementation part of machine learning algorithm. So here, these are the core components. I have already said that quantum data representation and quantum circuits are very, very essential. And we are giving the classical data, and the classical data are encoded to the quantum bits, qubits. So that could be done by three important encoding methods. One is basic encoding, which is used to represent the qubits in binary values. And the second one is amplitude encoding. So here the states of the amplitude, the probability of each quantum bits also represented in superposition state. So those amplitude values are taken and it is mapped to the data. So that is second one, amplitude encoding, and it is harder to implement comparing the basic as well as angle encoding. And third one is angle encoding. So here in the previous class itself, we have seen that reference angle, the base angle. So based on that, the quantum gates are implemented. So based on that rotation angles, we could also map our classical data. So these are the three important encoding techniques. And quantum circuits, we have parameterized quantum circuits or variational quantum circuits. So here the parameters are tuned to train like our neural networks. In neural networks, we have lots of parameters. That is number of neurons, the weights, bias, then the optimizers, then the gradients. Likewise, there are so many parameters are there. So each and number of hidden layers, so that are parameter tuned by means of this quantum circuits. And quantum gates are the primary component of quantum circuits. Here in neural network, you can use that one as a activation function. And these are some of the key algorithms and models in quantum machine learning. Quantum support vector machines. Here we will transform all the data to another plane, hyperplane. So here we can convert it into that is a complex part of SVM. So that could be done easily with the quantum computing. Then quantum neural networks, it's an analog of classical neural network. So here variational quantum computers circuits will be used in the layers, and quantum gates are used as an activations, and we can perform the operations also there. And next one is quantum k-means and the quantum k-nearest neighbor. So here the distance calculation is a main important complex component. So that could be uh, easily rectified or easily overcome with the help of quantum. These are in quantum generative advisory network is also there. I already said that GAN model we have two component, generator and then discriminator. Generator will always generate a false information, and the discriminator will always classify it is into correct or incorrect. So therefore, if we are using quantum generator there, immediately number of value or number of images can be, or images or any data can be generated, which could be used for with the help of quantum superposition state. So here this mainly used in image synthesis as well as anomaly detections. We are using this one, and this is the main pipeline of machine learning. In normal machine learning, we will get the data acquisition, data pre-processing, then we'll select the model, then train the model, fit the data. After best fit, we can use it for evaluation, testing, prediction. So here we are giving the classical data that will be pre-processed to improve the size, rescaling, cleaning, transformation, anything can be done. After that, the classical data is converted into data encoding by means of any of the three methods: normal, basic encoding, or amplitude encoding, or angle encoding. Then that quantum feature map is given to the quantum variational circuit or kernel evaluation. Then it uses an optimizer or classification kernel matrix using. Then they are using it for training the model, which either it could be a pure quantum classifier or it could be a hybrid one. Then we can use it for prediction. Finally, that is used for post processing and the evaluation of a testing environment. So one of the participant already requested this one: what are the tools and frameworks which supports quantum machine learnings? So these are the frameworks. So those who already used TensorFlow, this is also very easy for us. So here this is Qiskit machine learning framework, which is supports all the machine learning algorithms, which was developed by IBM's SDK, and this is also some of the algorithms are open source. Then Penny Lane, it is a new thing focused on hybrid quantum classification models, and it also using a differential programming concept. Next, the third one is TensorFlow Quantum. Here we are using a quantum ML extensions for TensorFlow, and this is CRQ. This is a product of Google, and we can also support this one in TensorFlow Quantum, TF Quantum. Then this is D-Wave, that is Ocean DSDK, which is a quantum annealing and optimization techniques. Shall I take 5 minutes break? After 5 minutes, we shall meet.
Yes, yes, ma'am. Yes, ma'am. Yes, ma'am.
Dear participants, stay connected. The resource person will join within 5 minutes.
Shall I continue?
Yes, ma'am.
Okay, so far we have seen the two important sections, that is machine learning as well as quantum machine learning, and these are the tools and frameworks which is supported for quantum machine learning. So I already said that IBM, Google, they are developing quantum computers, and they are doing researches on this deep learning machine learning components. So they offered so many frameworks and tools for free, so the researchers can use those things, and we can also compare with the method existing classical methods with the quantum machine learning methods. So the first thing we are going to see the normal classic k-nearest neighbor classification along with the quantum classic k-nearest neighbor. So here, this is a supervised learning algorithm, and here the main core complex component is similarity. So let us see this diagram here. The first part, it is k is equal to 5. So when there is a new data point arises, it will compare with all the data points in the data set. For example, if I have 1 lakh data points, the particular data test data is compared with all the 1 lakh other samples, and it identifies the most relevant top 5 closest sample, and then it will take the sample number of samples which belongs to a particular class. That class, it will also move on to that particular class. So here the similarity measure they are using, we can use different similarity measured based on our datas, Euclidean, city-based, Manhattan distance, Mahalanobis basis. Likewise, there are so many similarity metrics are there, and this is a time-consuming component within this k-nearest neighbor distance calculation. And for this one, it takes around a order of n distance for calculating with the nearest neighbors. So here, whenever a new data sample is coming, so this could be solved by means of quantum k nearest neighbor. Here the data points, here 1 lakh data points are there. So those 1 lakh data points can be represented in qubits, in number of qubits based on our computing facility. We can take the number of qubits, and in parallel we can check all the particular data point with all the things parallelly. If suppose I am using 2 power 5 qubit means we could able to do parallelly with all the uh, uh, distance can be calculated in parallel. So that can be done in quantum k nearest neighbor. So here the computer distance is a inner product which is efficiently done with high dimensional vectors. So thereby it reduces the polynomial exponential time to the logarithmic time. So here we need to convert this one. These are the key components: quantum state preparations, the converting the classical data points to quantum states. Either it could be amplitude encoding, or it could be uh, the angular encoding or basic encoding. But for this application, k nearest neighbor, amplitude encoding is a suitable one. So therefore, they have used amplitude encoding. Then they'll take the inner product estimation. Using this test, they'll calculate the inner product. Then after compute the distance between the test point and all the samples in the superpositions. We can keep all the data points, the sample data points, training samples in superposition state. So thereby we can able to compare, or able to take the decisions in parallel, and then we can take the decisions. K smallest decisions will be taken with the highest similarity measure, and based on a majority voting, we can push that particular data point to that class. So this is the classical classification decision, and this is the uh, coding. So here uh, it is implemented in Qiskit quantum machine learning framework offered by IBM. you can use any programming languages, Python or R language or anything. All the machine learning languages can be supported, can support for this one also. But the thing is, you have to import all the libraries which is available as a open source of quantum k nearest neighbor. Otherwise, we can take the pay the amount and we can take the proprietary softwares. So here, this is available in open source. So quantum Qiskit. First, you have to install Qiskit, pip install Qiskit, and then from Qiskit, you can import the QKN neighbors classification. So, which algorithm we are going to develop that one, and then encoding. So, for everything, the default, the inbuilt functions are available there. So, you can take it there. So for importing data sets, we can also use Skylearn or Skykit. So these are the basic function library files which we are going to use it for this quantum k nearest neighbor. And then we are taking the simulator. For using that simulator, you are getting the connecting with the quantum instance. You are getting the quantum instance from IBM. So for that applications, you are importing basic AER. So with that, we can connect with the quantum simulator, and how many instances we want and how many shots we can vary with the according to our data. This is the initialization of quantum instance. And third component is initializing the quantum k nearest neighbor model. So which model we are going to use? So if we are using traditional classification algorithm, we can take a KNN from Skykitlan, whereas this is available in Qiskit Quantum. If we are using other frameworks, we can also have similar functionality in other frameworks. So if time permits, I will show that one. So therefore, these are the thing that is initializing the identifying the variable quantum nearest neighbor classification and mention the number of neighbors, 3 or 5 or anything. Then we have to assign those instance to the quantum instance. So this is the initialization part. Next, we have to load our data set. So like our previous machine learning models, after importing all the libraries, we need to load the data set, isn't it? So here we are going to use with the iris data set, which is having